So we are asked to evaluate these expressions without using a calculator, which is great because, first of all, we haven't talked about how to put these in the calculator, and we've got all kinds of different bases, but it requires us to think through some things in kind of a weird way. So look at each of these pieces individually. So if I have log base 3 of 9, the way to think about this in exponential form is 3 to the what is 9? To the 2. So log base 3 of 9 actually equals 2. Log base 2 of 8, 2 to the what is 8? 2 to the third. Log base 4 of 116, that's the same thing as 4 to what power is 1 over 16? Negative 2. So to simplify this expression, we're looking at 2 plus 3 minus negative 2. What is 2 plus 3 minus negative 2? 7. Okay, so they look super complicated. They're not as hard as they look. The one on the right is very similar, same kind of vibe. Log base 5 of 5. 5 to what power equals 5? 1. Then we've got our log base 5 of 125. 5 to what power is 125? 3. Last one's probably the trickiest one. We've got the natural log of the cube root of e. So this is the same thing as saying log base e. How can I put the cube root of e as a exponent? E to the 1/3. So log base e of e to the 1/3. So e to what power is the same as e to the 1/3? To the 1/3, right? If I switch this around to exponential form, this is e to what power equals e to the 1/3? It would just be 1/3. Ooh, I'm going to do that one slow. There we go. Hang on. I'm going to switch this and do this in multiple colors. So I'm changing it. So log base e, that's what natural log is. And then we have our e to the power of 1/3. And we want to know what this equals. Equals some number. So if we switch this around, base of e to some power question mark equals e to the 1/3. My argument. This is one chunk. So what does question mark have to be for e to the something to equal e to the 1/3? It's not negative 3. It's 1/3. Negative 3 would be if we had 1 over e cubed. The cube root, that's when it's a fraction. We need our index. So this whole piece here equals 1/3. So watch out for these. They get a little tricksy sometimes. So when we're looking at this statement here, we have 1 minus 3 plus 1/3. What is 1 minus 3 plus 1/3? Somebody got music playing? I hear something. What is 1 minus 3 plus 1/3? One minus 3 is 1 minus 3? Negative 2. Negative 2 plus 1/3. Negative 1 2/3. So I owe you $2 and I give you 1/3. So now I owe you 1 2/3. Or you can do it as a improper fraction. -2 would also be known as -6/3 plus 1/3. We'd have -5/3. I genuinely do not care if you write it as mixed numbers or as improper fractions, whichever way works better for your brain. Okay, so the evaluating without a calculator, look at each piece individually to find the number that represents that logarithmic statement. Then combine together. Okay? Okay, so let's look at those two kind of story problems that we've got there. On that page, there's a lot of paragraph here. Theoretically, this is a real thing. I do not know enough about photography to know how accurate this is, but this is theoretically what that is. So there's a formula that represents the f-stop setting, which is a thing where P is the measurement of the sunlight, and the N is our f-stop setting. So we want to know what her setting should be if they've measured it as 16. What can we do? I know this formula. And the sunlight, which is P, is measured at 16. What do we do? Substitute in. I know that P is 16. That's what they've told us in this paragraph. P is 16. So we want to find N. So we have log base 2 of 16. Yeah. Because I'm going to switch it around. We get 2 to the something equals 16. So our N equals 4. So she should put it on setting 4. Totally know what setting that is and totally know what that means. Oh, boo. Not a coffee. Okay. Questions on that one? Boop. Which is why I printed these out, because they were really short. Yep. Yeah, the calculations on these are really short. I knew it was going to take us way longer to write the paragraph down than to actually do these. All right, another very similar one. We're given a formula for how we calculate the atmospheric pressure P based on the altitude x. So we got that the opposite of x is the natural log ln of P. So we're asked to find the pressure when our altitude is half a mile. So if I know we're at half a mile above sea level, what are we going to substitute that in for? For x. X is our altitude. So we're going to substitute it in for x. So we have that the opposite of our x, which is 1/2, equals the natural log of the pressure. I could also write this as our -1/2 equals log base E of pressure. So it doesn't matter how you write it, but if you struggle to remember that log base E part of it, that might help. Because the easiest way to solve this one is to switch this back into exponential form, because my base is what? What's the base? E. My base is E. What is the power? -1/2. And it's going to equal which piece? P, our pressure. So E to the power of -1/2 equals the pressure. That's a type it in the calculator situation. E to the -1/2. What is e to the negative 1/2? Give me 4 decimal places. This step is when we type it in the calculator. We cannot do e to the anything and get a decimal. Hello. Calculator. There we go. I forgot the late part of it. It was just calculor. Honestly, sounds like a really good comic book villain. It's calculor. We cannot get decimal values of e to the anything without a calculator. You have to. You have to. Okay. Questions on that one? We're going to keep practicing solving like this. It's just not going to have near so much paragraphy context. So here's 2 more very similar solving things. So we've got log of x squared equals negative 4. So what's our base on this one? 10. This is our common log. So this has a base of 10. If there's not one written, it's base 10. So in order to solve this, probably it's going to be easiest if we switch this back into exponential form. So we said our base is 10. 10 to what power? Negative 4 equals x squared. Switching it back around to our exponential form. Well, this we can do. 10 to the power of negative 4. What is 10 to the power of negative 4? As soon as a fraction, yeah. Yeah, 1 over, and it's 10,000 because it's 1, 2, 3, 4 zeros. Whenever you have tens, that's an easy way to do it. Mm-hmm. So we want to know what x is. Uh-huh. I'm sure I did it right now. What do we get? 1 over 100. What are we forgetting? Plus or minus. Whenever we square root both sides of an equation, that's when we get our plus or minus. So it could be positive 1/100th or negative 1/100th. Either way, we would get the same answer. Okay. So the next one is a little bit tricky and requires us to remember some of either the properties from yesterday or all the way back to when we learned logarithmic properties back in Algebra 2. Because this has a natural log stacked inside of an e. So I'm going to put one of the properties we had up on the list yesterday up here, where we had a to the p log base a of c. I'm just going to give it a letter. C to the p. So this is a property that we had yesterday. I think it used different letters, but honestly, I didn't write it down with the exact letters you had. Where if we have a base here and a log inside here, they're going to wind up canceling out with this thing being a base and this piece out front becoming a power. It's using the power property of logarithms from back in the day where our coefficients come up and become powers, which we'll talk about those properties tomorrow, maybe later today, depending on our time. So it's using an old logarithmic property that we're going to work with, but they're giving it to us in kind of a strange time. So this piece is going to go up and become an exponent on the 3. And then the e and the natural log are going to cancel out. They are inverses of each other. E being raised to a power is the inverse of the natural log argument. So this is going to become 3 to the power of x, which equals 27. So it's using this property that we had yesterday in that big old list of properties. And we're going to practice with that a few times before we move forward. Because it's weird and awkward and it feels like it comes at a very strange time. And I agree with that, but I mean, we get it. So 3 to the what is 27? 3 to the third. So our x has to equal 3. There are a couple of ways to do this. You could just switch this into logarithmic form, and then you're going to wind up with ln of 27 divided by ln of 3, which you can do in the calculator, and it should come out as a 3 exactly. But I wanted us to see this property because they ask us to use this a lot of times in the homework. We're going to practice with this property again, but questions on this one right now? Okay. Because the way that they have us use this property a lot, and it looks like a paragraph, I promise. It's just that the instructions and the equation are mixed together. They use this property a lot for these kinds of questions where they're going to give us an exponential growth and they want us to put it as a base of e. So we have this equation here. I've got my f of x equals 50 times 9 over 8 to the power of x. And they want us to write it with a base of e. So I'm just going to copy the equation down here just so I have everything in one row. So f of x equals 50 times our 9 over 8 to the x. And our goal is to make this have a base of e. So we're going to use this property, but we're kind of going backwards. We're going to start with a piece that's exponential, and we want it to have a base of e here. So I want this to be an e. So I'm actually going to rewrite this property with an e instead. So we have our e to some power p with our log base e. So this is going to have to be an ln of whatever that x is our x to some power. I don't like them using x's here, but we'd use what we got. So we want this piece to be the base of our exponential piece here. So that's going to wind up here in this exponent. And whatever the power is I had here, this guy here, that's going to become the number in front. I don't like that those are so close together color-wise. Let me get a different color. There we go. There we go. That's a better different color. So the 50 out in front really doesn't do anything. It's just going to plop down. This guy's just dropping down. He's not doing anything. We are trying to change this piece. So we're going to make it have an e. But that means I have my ln of the whole chunk up there. So the power is going to be in the front. That's going to be that x. Then we're going to have the natural log of the base, that 9/8. It's taking this piece here and having it be this side. And this left side chunk, this piece is what we have in here. I know we don't know why the heck we did that, but questions on what we did right there. Because it's weird and super awkward. Because the reason we're doing this is we want to be able to express this equation like it's a PERT equation. Our principal times that base of e to the RT. And what they want us to find, what they're trying to get us to see here, is this R, which is going to be whatever the number is that's next to my X. So we're not looking at our X piece here, we're looking at that natural log of 9/8. So our R is going to equal that natural log of 9/8. We want that as a decimal, so we're going to type that in the calculator. What is the natural log of 9/8? So I'm going to take 3 decimal places. Our 0.11 rounds off to 8 is about the rate here. So if we were looking to find the percent of change, our rate of change, this change is at about 11.8%. That's what they're looking for here. It's taking an exponential function that has a multiplier as a base and making it be a continually compounded exponential problem. We're going to practice it again because I know it's weird and awkward. Questions on the first one? Okay. Same thing. We're going to write it with a base of e to get the growth rate. We're trying to find R. So I'm going to bring my function down. My f of x is our 100 times the 1/2 to the x. Yes, dear.
So what is x? Which one is x?
This x up here? Or this one over here? This one over here. So this is whatever the base of our thing is. I'm going to switch that. I'm going to make that be a b, just because I hate this. I don't like having 2 x's in the problem. I'm going to switch that to be the letter b, because that is the base of this exponent here. So we're going to have a base and a power. Bless you. So we're also specifically told to make this be e. So I'm going to rewrite this with our new letter here as an e thing. So this is e to the power of whatever our p is, log base e, so that's my ln, of whatever the base of my exponential piece is. And that means the exact same thing as whatever b to the p is. B to the p. So in our little statement here for our equation, what is the b part? The 1/2. What is the p part? In this statement? The x. Too many dang letters in these things. So this guy's just sitting to the side. This has no impact on this first part of it. This is only relevant when it comes to the part. So we have to get it to an e first. So this guy's just going to drop on down. So my 100's just hanging out. But I want to switch this thing to be to a power of e. So that's when we use that formula to the right. So our e to the power of, what's going to go in front? X natural log of 1/2. So we've switched it around. And then what we're doing is we're comparing it to PERT, our P e to the RT. Why am I not saying that my R is my X?
We don't know.
Because the thing we change is the time. It's not going to be that I have this account for 6 years and it's my rate that changes. It's that I have this savings account, or I have this problem, I have this situation, and it's the time we're looking at. We're looking at different times. So my variable is going to be the T every time. So what is our rate on this one? Our natural log of 1/2, which is about what as a decimal? Negative 0.693. So it is decaying at a rate of 0.693. Yes, dear.
If you look at Precal with this and 5.4, how many questions are going to have something like this?
I'm going to say there's not usually tons that do the same kind of question over and over again, unlike a quiz or a test.
Are we doing graph sheets?
Huh?
Are we doing graph sheets?
We will graph exponential functions. We will graph logarithms. We're not going to switch exponentials to base E and graph that. So we're not going to graph these specific ones, but we are going to wind up doing some graphs. Because we need to be able to graph logarithms and all that jazz. So I know these ones are awkward and weird. It's mostly using this property over here, which if it helps, switch it to be base E and just have another version of it here. Totally fine. This is one of those ones that IU put on the list of questions, so we wanted to make sure we hit this because it could wind up showing up on the final.
What is
E,
What is A?
A here is just whatever the base is that you want your log to be. So we just want it to be E because they specifically asked us to put it as a base E. But if I wanted to have a base of 10, I could do that. If I wanted it to have a base of 3, I could do that if I wanted to for some reason. You can use whatever base you want. It's just most commonly we're going to make something have something we have a button for on the calculator. So we will wind up using base E in natural log or base 10 common log most frequently, simply because those exist on calculators.
Will we get like a cheat sheet with the special?
Nope. Specifically, we're not allowed to give you anything for the chapter tests. When we get close to final, I will get all the things we need for that. Okay, questions on this one? All right, our last bit of this part is we are going to graph some logs. So I'm going to pass you guys some graphs. We're going to start with log base 2. They're low curly because they keep getting this out. And we're going to hopefully do 2 graphs, hopefully. We should be able to do 2.
What if there is no elevator and it's actually just some staircases?
I think it's a ground. If I was using my outside, I would say the ground.
But say that one.
Alright, you can have it.
Is it on your own work?
Alright. So, what do we know about logs? Aside from we hate them. They're the inverse of our exponential functions. So when it comes time to graph a log, we're going to need to remember that they are the inverse of exponential functions. This one, log base 2, is specifically the inverse of which exponential function? 2 to the x. So this is the inverse of this. when we are making logs, we're going to use that information because we've worked with exponential functions before. That's when we take our x values to find our y values. And we want that good view of the middle. So we use our -2, -1, 0, 1, and 2. And if we're looking at 2 to the x, what do we get as our y values? What is 2 to the -2? 1/4, 1/2, 1, 2, and 4. And where does this have an asymptote?
Zero.
More specific. Y equals 0. Yes. So when we are looking at our log, so this is our exponential. So when we're looking at our log base 2 of x, I take everything that was in the x column and put it in the y column. Everything that was in the y column goes into the x. Everything that was an x becomes a y. Everything that was a y becomes an x. We switch them. So my y's are going to be -2, -1, 0, 1, and 2. My x's are going to be 1/4, 1/2, 1, 2, and 4. And instead of having my asymptote be y equals 0, x equals 0. So my asymptote is switching from being a horizontal asymptote to being a vertical asymptote. It's going to be like that. And we're going to plot up our points. And we're just going to have to be careful because my x is 1/4. My y is -2. I'm going to get a different color. Thank you. My x is 1/2. My y is -1. X is 1, y is 0. 2, 1, and 4, 2. Ooh, I'm going to get that to be chunkier pen. We plotted up our points?
No, like this.
Oh, the asymptote?
Yeah.
So since exponential functions have one at y equals 0, everything that was an x becomes a y. Everything that was a y becomes an x. X equals 0. So we have a vertical asymptote instead of a horizontal asymptote. So what's our domain for this function?
Zero
0 to
to infinity.
infinity.
-infinity to positive.
And our range, that's from our -infinity to positive infinity. So we use the fact that logs and exponentials are inverses of each other to help us make our tables. It makes our life way easier. Okay? Questions on this part? No, I did not hand you a single graph. Because we got to be able to do transformations. All right. This will be our last one for today. So we have log base 2 of x minus 4 plus 1. So I want us to think about our transformations, our old school style transformations. What's our h going to be?
My bad.
H is going to be 4. That's the one that's always inside parentheses and the opposite of the sign. What's our K? 1. It's the one added on the end. So we're going to use that when we make our transformations with our x plus h, ya plus k, those kind of guys. But we got to get our parent tables before we can do that. So these will be used in like the very last step. Our first thing we need to know is we need to know what is our base. What is our parent function? 2 to the x. So I'm going to start with my 2 to the x, just like we did on the last one. I'm just going to make these very skinny because we're going to have 3 tables here. So my parent function for my exponential, that's the same one we just did, where we have our -2, -1, 0, 1, and 2, and that gave us our 1/4, 1/2, 1, 2, and 4. So there's our 2 to the x, and it had our asymptote at the y equals 0. Then we're going to make our parent function for our log base 2 of x. That's the one we just did. If you want to do that either all in one go, or if you can do that switch while you're writing it down, again, I only look at your tables if I can't figure out what happened. The tables are a tool. So if you can start here, which I know some people will be able to, some people won't, that's totally okay. Log base 2, I've got these switched. So my y's are my -2, -1, 0, 1, and 2. And my x's are what used to be my y's, my 1/4, 1/2, 1, 2, and 4. And we'd have our asymptote at the x equal 0. Ooh, there we go. So to graph our transformation, that's when I'm going to take my parent function for my log and apply my h and my k. We're going to take our x's plus h, y times a plus k, just like we've done for all other kinds of transformation forms. So I'm going to take my x values and add 4. My y's, I don't have any number multiplied out in front, so it's times 1 plus my k plus 1. So I'm taking all my x values plus 4. So 1/4 plus 4 gives me 4 1/4. 1/2 plus 4 gives me 4 1/2. 1 plus 4 gives me 5. 2 plus 4 gives me 6. And 4 plus 4 gives me 8. And then also, since our asymptote down here was an x equals 0, we need to add 4 to that. So my asymptote is actually going to be at x equals 4. Since it's an x, it also gets the h added to it. My y's, we need to add 1 to. So -2 plus 1, -1. -1 plus 1, we get 0. 0 plus 1 is 1, and then 2, and then 3. So we're going to have our asymptote at our x equals 4. So that's over here. And we're going to plot up our points with our 4 1/4, -1, so somewhere there-ish. 4 1/2, 0, somewhere like that. 5, 1, 6, 2, and 8, 3. So we approach our asymptote this way, and it continues up that way. Whoop. Okay. Question mark or questions on that one? All right, you got 2 minutes. Haha, we made it as far as we needed to. I think that date for the quiz is wrong.
That homework is a little long.
They're, I believe, very short questions. I think that one took less pages. Yes, but you don't need lines to them. Like, it's a lot of stuff, but it only took me 2 pages. And I leave a lot of space. Alright, so that got us up to where we needed to be. For that one.
Did you just say, shut the heck up? I don't know what's going on. Is that something? Yeah, I actually think it's so you said shut the heck up, stupid MF. No. That's so mean.
I said MF because I said, like, not MF.
Whatever, Justin, whatever. What, Metso 14.
Cool.
Boy.
Ah!